In this sequence of videos, we're going to talk about privacy. So we'll start off kind of high level, talking about, like what are some definitions, what are some concerns and trade-offs that might come up in dealing with privacy. Then we'll talk about some specific examples of attacks, right? Ways that people's privacy can be violated in data sets, that sort of thing. And then we'll talk about a couple different techniques for actually achieving privacy. And they're kind of different in that one will be focused on privacy in the process of data collection. The other will be privacy in the process of querying a data set that may not necessarily be private. And kind of all over all this, we'll think about this idea of differential privacy, which will introduce, and it's essentially a mathematical notion around an algorithm that's private, and private meaning that we can't tell whether an individual is or isn't in the data set. Hope you enjoy. So I want to start off by talking about sensitive data, where it comes from, why it matters, and then kind of from there go into what we might do to keep some of that data private. So a lot of data science, a lot of applications of data science require the use of sensitive data. This is maybe most obviously true in like a medical healthcare setting where maybe you're trying to understand the efficacy of some treatment, you're trying to understand the progression of some disease in a population, and you need data about individuals that has confidential medical information that obviously you don't want to disclose more broadly. But it's also true in other applications. Say you're the government, you're trying to collect data to help understand the effect of some policy or some intervention, whether or not the government should implement some program. And you go out and collect census data, you go out and collect survey data, and some of those attributes may be sensitive or private, or people might not want those disclosed for any number of good reasons. This is also true, in other applications too. You think about your smartphone, apps that you use on your smartphone are constantly collecting a lot of data about you that they use to, get information about you, show you ads, get you to click on their ads and make money that way. Advertising companies do this as well, by reading email, understanding the history of videos you watch. And a lot of that information is useful for their business, but it's also useful for their business to keep it private, right? They don't want to have that information leak because then that'll reduce trust in their system and you won't use it. So in general, there's many applications that require using sensitive data, but also require the use of privacy. It's true also, like you can think about wearables, like a smartwatch or some other kind of app, financial data, things about credit scores. And so with any application, there's always a risk-benefit trade-off. Right? The sort of safest thing you can do from a privacy standpoint is pretty much always don't collect the data, don't analyze it, don't use it at all, right? That's probably the safest, most private thing you can do. And in some applications, the trade-off of gathering the data, storing it, might not be worth it, but in many applications it is, right? There's some real benefit that can be provided. And what might that benefit be? Well, you can imagine in a population medical study, the benefit might be, you collect a bunch of data on people's genetic information and you want to understand like if there are any genetic underpinnings to rare diseases. The risk is a violation of privacy, right? You may have your information, your private medical information released, but the potential benefit is improved medical care, right? A better understanding, scientific understanding of medicine, a better, potential for better treatments for rare diseases, or even common diseases, or, any number of medical advances that may come out of this. Of course, there's a second order risk of like, well, then, if your data is in this database and you have this, genetic variant that makes you more predisposed to something, then maybe an insurance company can discriminate against you based on that, right? So there's like risks and benefits and then more risks. And then there's other applications. For example, there are facial recognition companies that go out and scrape social media websites, the internet, to find images of people's faces and who they are, right? And there, obviously, the risk is a violation of privacy, right? You have this data confidential, presumably what people presume to be like, well, I don't want all these images of me in your database. And so the risk is that you have this sensitive information in your database. The benefit is that you can provide facial recognition technology. Now, a lot of the applications of facial recognition technology end up actually violating privacy, and in many cases, violating human rights. So maybe the benefit isn't such a benefit after all. So it's important to think carefully about what the risks and benefits are of building any technology, and kind of keeping that in mind before jumping in and saying, oh, we'll apply this differentially private. That being said, the techniques we're going to learn about today are really useful in cases where you have decided that there is a real material benefit, but you want to mitigate some of the risks. Okay, so we'll talk a little bit more about how we can do that in the next few videos. What kind of data is private or sensitive anyway? So the kind of standard definitions that people use are things called personally identifiable information, PII, or there's also protected health information, PHI. And there's like technical definitions of these that if you do any work with this kind of data, you have to take training that kind of teaches you exactly what it is and how to protect it and so on. But generally, you can think of PII as any sensitive identifying attribute. Somebody's first name and last name, or their where they live, their date of birth, social security number. Those kinds of things are all personally identifiable information. And a lot of times, most regulations that protect privacy tend to focus on things like PII. And so, the kind of simplest thing you might think of is, well, okay, you have a data set with a bunch of people, and let's just delete all the columns that contain PII, right? Get rid of all the columns that have somebody's name, social security number, email, any of that. Just delete the columns and keep the rest, right? You're essentially anonymizing the data, and maybe that'll help. Spoiler alert, and it turns out that it actually is not enough. In the next few videos, we'll talk about a bunch of examples of why. But even then, a lot of cases, people do store PII. It's super common for this information to be leaked and breached. Actually, as as we're like in the middle of this right now, the University of California has had a huge leak of a bunch of PII from a whole bunch of student, staff, faculty. Information has been leaked. Is available. They're encouraging people to get credit freezes and all this. So this kind of information is very sensitive. Malicious actors can use it to, take out loans in your name, to find out information about you, to impersonate you, to do any kinds of things. So this kind of information is very sensitive by itself. And then on top of that, even data sets where you remove it is not enough. Why is it not enough to just like delete the columns that are identifying, right? Like, why can't we just delete the columns for like first name, last name, email address, like anything that would individually identify you? Just get rid of it, anonymize the data set that way, right? Maybe we can keep date of birth because, April 24th, 2021, there's a bunch of people being born on this day, right? So that's not necessarily identifying, right? And zip code, there's a bunch of people with the same zip code. Like everybody in Berkeley has the same zip code. Well, one of a few zip codes. So like we'll just keep those in, right? And same thing, like sex. Maybe there's lots of people who have the same sex. We'll just leave that in. But we'll get rid of like name. We'll get rid of email address. We'll get rid of anything like that. Anything really private, right? Maybe even like street address, right? We'll get rid of that because that's very identifying. Is that enough? Well, it turns out it's not. And so for an example of why not, we're going to talk about what's called a linkage attack. And to illustrate this, we'll go through what Harvard researcher LaTanya Sweeney did in 1997, which was to say there's this medical data set that was released with a bunch of anonymized medical data, right? Like people got rid of the names, and this is back in 1997. Got rid of the names, like I just said, right? Like name, street address. Instead, all the medical data had was like some broadly identifying stuff like zip code, date of birth, sex, ethnicity, and then like medical stuff, right? Like what information about the visit, like the doctor's notes, maybe the diagnosis, like what kind of medications. And the idea was releasing this data would help researchers maybe find patterns or connections, or by releasing this data set, you help researchers do more interesting scientific analysis and understand medicine and science better. And so by anonymizing it, we get rid of all the problems with privacy, right? Well, it turns out not so much. What LaTanya did was she went to a publicly available voter list. And this is available in Massachusetts, but is available, I think, in most states, where it has a list of all voters, and it has their name, their address, what date they registered, like what party they're affiliated with, the last time they voted. And it also has zip code, date of birth, and sex. And what she did was she went and found the Massachusetts governor on that voter list, right? And I mean, it's easy to find somebody because it has all the name, right? You can just look up their name and their address and all that, and you can find somebody. And then you say, okay, what's this person's zip code, date of birth, and sex? Now go to the medical data and see if there's anybody who has the exact same zip code, date of birth, and sex. And what she found was there was exactly one person in the medical data set who had that exact combination of information. And of course, that was the governor. And so by doing this, she exposed all of the governor's private medical records through this, anonymized data set that was actually not anonymous. So this kind of thing is called a linkage attack, where you basically combine multiple data sources, maybe like some private or anonymized or some like public, and you combine those to re-identify or like de-anonymize, these are common words that people use, records in some private database. And there's like a whole bunch of schemes kind of like this. But if you do some like kind of ad hoc anonymization like this, then you're probably going to be vulnerable to this kind of attack. And a similar idea is, like let's say that you're organizing a survey. Let's say you're surveying, data science students, and you send the survey out to everybody in the data science program, and everybody fills it out. And then when looking at the results, you say, there's like a lot of people, you don't ask for name, you don't ask for anything like, but you want to know like just people of a certain year. Do seniors feel differently than juniors or than sophomores and so on? And you also want to know like demographic information, right? Are certain people from certain underrepresented groups, is their experience different? And so you ask, like, are you a member of you ask for things like sex, you ask for things like gender, you ask for things like sexual orientation. And then you find that, hey, look, it turns out that there's exactly one person with this exact combination of attributes, right? Like if I'm filling out a survey, maybe I'm the only person at Berkeley who is a lecturer, who is South Asian, who is in this particular age bracket, who is employed by the Division of Data Science, and has taught this many times in the last 5 semesters, right? Even though that none of those are like have my name on them or identify me, it turns out I'm the only person with this combination of attributes. And that's the same idea here, right? That the governor was the only person with that same combination of attributes. And so one thing that was proposed to kind of get around this was this idea called K-anonymity, where you divide data into these like quasi-identifiers and sensitive attributes. And for every like combination of quasi-identifiers, like gender, age range, sexual orientation, like there's a limited number. And for every combination, there has to be at least K rows of data, right? That way it's not like there's only one person who has it. But there's a whole bunch of variants that have been proposed on this. And they're useful in some contexts, and these are actually used in a bunch of places. But there are attacks that can still be used, right? Like let's say that there's a bunch of people who all have the same. Let's say you're doing a study on political views, and maybe it's like some political view that's maybe not necessarily predominantly popular, and you have a survey, and everybody in this particular demographic answers the same, right? And so you don't know who each of the individuals are, but you know that everybody who has this combination of identifiers answered the question the same way. And therefore, I know that if you have that combination of identifiers, then you must have answered that way too. This is a problem with schemes like this. They're generally vulnerable to these sorts of attacks. And so, next, we'll talk about some more examples and also ways to define privacy or build privacy that are not so vulnerable to this. So now I want to talk about a different kind of attack that can be used on data that maybe is a little more carefully constructed, right? It's aggregated to avoid privacy concerns. So we're going to look at genome-wide association studies, or GWAS for short. And what these are looking at is variation in a population of the genetic information for every individual. And so it focuses particularly on specific locations in the genome And at these locations, you basically either have a major variant, which is, like the more common version that more people tend to have, or you have the minor variant, which is like flipped. In this image, for example, this person has this base pair here, this other person has this base pair here, right? Don't worry too much about the genetics. The big idea here is that, in these locations, it flips, right? So this person has the more common one, this person has the less common one. And the way these studies work is the NIH or whoever's running the study takes the DNA of like 1,000 people who have some particular disease, right? And they're interested in understanding, is there some genetic information in people who have these disease that can help us understand where it comes from, how it develops, like, are you more likely to have it? Should we do preemptive treatment and so on? And so what they do is, they don't release all thousands, the information for all 1,000 people. Instead, they just aggregate. All they do is they do a total aggregation where they say, for this test population, at each location, how common is the less common version, right? So in other words, like if CG is more common than TA, then for this population, what percentage of people have this less common variant? And that's essentially what we call the minor allele frequency. And so at every location in each of these 100,000 positions, you get some number between 0 and 1 that says, in this test population, what percentage of people have this less common variant on the gene? And the goal is to find some association, right, between the minor allele frequencies in each location and any disease that may be present. So this seems like pretty safe, right? It's like aggregated data. You're aggregating over 1,000 people. You're not releasing anything about the individuals. Seems like it should be a safe way to release data, right? Well, it turns out that there's actually an attack that you can do on this data. And what the attack you can do is you can infer whether or not a person is a member of that test group, right? Whether is a member of that group that had the disease. So in particular, let's look at the blue, which is the data for the test population, and the red, which is the data for the overall population, right? And so this red data is public, right? There's this data set called HapMap that has the overall frequencies for the entire population, right? And so like at location 1, the less common variant occurs in 1% of people. Location 2, the less common variant occurs in 4% of people, and so on and so on and so on. But in the test population, right, the people with the disease, the frequencies are slightly different. Now, the thing is, you have 100,000 different locations here, right? So I have 100,000 different chances where the blue and the red could be different. So now let's say I take an individual, right? And I take this particular individual, in this case, it's Moritz, right? Professor Moritz Hart. And I look at, well, let's look at each location, right? Whether or not this person has the less common version, right? And so here I see no, right? Aha, so this is no, so maybe they're more likely to be in this group where it's more common. Here, again, no, so maybe they're more likely to be in this group where it's more common. Here, more likely to be in this group. And so what we do is, if we aggregate over all 100,000 locations, and for each one we see, hey, based on this, you look a lot more similar to the test population than you do to the reference population. And if you only have 3 readings, then it's like, well, you're kind of shooting in the dark. But if you have 100,000 different chances, odds are pretty good that you can infer whether or not this person is in the test group, right? Based purely on the differences between these values, right? In the test population, this occurs in 5% of the people. In the base population, it occurs in 4%. So that means if you have this, then you're ever so slightly more likely to be in the test population, right? And kind of same, if you do this like 100,000 times, ever so slightly adds up to pretty likely or pretty not likely. So this kind of attack can happen even on aggregated data. So, even if you are careful, you aggregate, there's still attacks that can happen on these data sets. So if anonymizing the data doesn't seem to help and aggregating the data doesn't seem to help, then what can we do? Is there any way we can have some kind of privacy guarantees in our algorithms? Well, it turns out that there are a few different ways we can go about it, and we'll talk about two of them. One is kind of on the side of when you conduct the survey or when you gather the data, and the other is on the side of when we analyze the data. And so to talk about the first one, it's called randomized response. And the idea here is very simple, and it's exactly what the name sounds like. So let's say that I'm conducting a survey and I'm asking some sensitive question. Maybe people, maybe the response, a particular kind of response is stigmatized or illegal or embarrassing. And so I don't necessarily, trust that people are going to respond truthfully. And also I don't want to be collecting this data and having private information about responses to this, potentially illegal, embarrassing, stigmatized question. To take an example, let's suppose the University of California is conducting a survey, a study on how many of its staff, students, faculty use, controlled substances, right? Drugs that are illegal under federal law. So, they go up and they call, they randomly pick a bunch of people, they call, email, reach out to them and ask, in the last 30 days, have you used any illegal controlled substance, illegal under federal law, right? Which includes like cannabis, marijuana, includes, harder drugs as well. And so you can imagine that people might not be inclined to respond truthfully, right? If you're using, a substance that's illegal, you probably don't want your employer to know about it. So, if somebody's answer is no, then yeah, they're probably going to respond truthfully. But if somebody's answer is yes, then you don't know if they're going to be responding truthfully, right? They may lie. So then in that case, how do you actually collect this data in a reliable way? And also, how do you ensure that people's responses will be private, right? If I'm the University of California running the survey and I'm a researcher who's interested in this data, I probably don't want to be storing a table that has, every employee and then like their answer, because, if somebody else gets their hands on that, if that data leaks, then it could be a problem. So what do I do? Well, instead of just asking the question, let's say I do the following. So when I call up I'm running the survey and I call somebody up and, I say, hey, in the last 30 days, have you used any illegal controlled substances? But instead of saying, don't answer yes or no, instead what I want you to do is I want you to first randomly choose a number between 1 and 10. If that number is less than or equal to 6, then I want you to respond truthfully. If the number is greater than 7 or more, I want you to flip your answer, right? So if you're going to say yes, say no. If you're going to say no, say yes. So now what we're doing is we're asking each participant to randomly flip their response, right? There's some certain probability with which they flip their response and say the opposite of, the actual answer. And as long as, presumably if that probability is less than 0.5, then maybe things don't look so good. But as long as that probability is, greater than a half of telling the truth, then maybe in aggregate, we can do something interesting with this. And this is exactly randomized response, where for every time you ask a question, you have the participant with some random probability flip their answer. And so now if I'm taking the survey, I can say, they ask me to go through this process and I say, yes, yes, I have, right? Then on that case, the person conducting the survey doesn't actually know whether it's truthfully, yes, I have, or like maybe my answer was no and I randomly flipped it, right? So even if I answer yes, I have plausible deniability about whether or not the answer is yes or no, right? And this is true for any kind of question that you may not want to answer, that you may want to keep your response private. This kind of method is pretty useful. And so now, how do we actually go about analyzing this kind of data? So let's say I go out and I collect a large number of responses to this question, right? And I'm the University of California. I do this survey, and it turns out that again the protocol was with 60% chance they answer truthfully and 40% chance they flip their answer. Now, let's say that I collect a bunch of data and 60% of people say yes. Then what does that actually mean for how many people actually use drugs? Well, let's think about this. If it turns out that 100% of the population uses drugs, right? Their answer would have been yes. Then in that case, let's say I take that 100% and 60% are going to answer truthfully and 40% are going to flip their answer, right? Again, randomly. So it's not going to be exact, but on average, 40% will flip their answer. And so that means what I should expect to see, if it is in fact 100%, is a response rate of 60% yes, corresponds to 100% of people truly saying yes. Now, let's suppose instead that I go and I collect this data using randomized response, and instead I see 40% of people said yes. So what does that mean for like the true fraction of people who actually would have said yes if I had just asked truthfully? Well, in that case, let's think about this, right? If we have, let's say everybody's answer was no, right? If every single person's answer was no, then that means, again, 60% of them randomly, right, would be responding truthfully, and 40% of them would be flipping their answer to yes. And so that means that basically my responses now I should expect to see response, yes percentages between 40 and 60%. Right? So somewhere in that range is what people should be, is what my average responses should be. And so anything in between that then 40% corresponds to 0, 60% corresponds to 100, and I can kind of interpolate in between. And you'll do this a little more formally on a homework assignment, and you'll see a simulation for this in discussion as well. Okay, so now let's talk about a kind of formal mathematical idea around algorithms, data sets, privacy, called differential privacy. And what's the intuition here? Well, remember in that GWAS example, we saw that we could like identify, this one person is in the data set. But in the randomized response example, we saw, well, like this whole process is random. If I remove one person's response from my data set, one row of data, then I'm probably going to get roughly the same result because like there was a 40% chance that they flipped their answer anyway. So this idea that my algorithm shouldn't be too sensitive to like removing one person from the data set, or essentially one row out of the data, is called differential privacy. And to be a little more formal, the definition of differential privacy is roughly this. So let's say we have some data set. The data set is fixed, right? So in this case, there's no randomness in the data set. And we have some randomized algorithm we'll call it A. We have A of D, and maybe A is like, take the data and compute the mean, compute the average percent. Maybe A is, train a random forest. But the key is that A has to be randomized. So you have some data set D. We have, use some algorithm A to get some quantity of interest out of the data set. And this algorithm A is called differentially private if for every event S, and this every event S is just a fancy way of saying, well, maybe the algorithm gives a result of 70% of UC employees use drugs, right? I made that number up, but there's some algorithm that produces that result, right? And if we say the probability of getting some particular result is roughly equal to the probability of getting that result for some other data set D prime. And what is this D prime? So D prime is a neighbor of D. It's a neighboring data set. This is kind of the language we use in differential privacy. And what does neighboring mean? It just means they're the same, except for one row, right? So D and D prime essentially differ by one row, right? One row has been removed or added between them, and so they're neighbors. And this probability is roughly the same. And to make this a little more formal, we can introduce this idea called epsilon differential privacy. And what this says is that the probability that A of D gives me some result is less than or equal to e to the epsilon times the probability that I get that same result from D prime. And what does this mean? Well, if epsilon is really small, right, then you can think about like the Taylor series expansion of e to the epsilon is like 1 plus epsilon plus like something epsilon squared. And those are all going to be like super small if epsilon is close to 0. So you can kind of think this is being pretty similar to like 1 plus epsilon, right? So the probability that A of D is in this set S is going to be very close to e to the epsilon times this. It's essentially like 1 plus epsilon. It's a factor of 1 plus epsilon, or a factor of e to the epsilon off. Why do we use e to the epsilon? It's because it makes the math work out a little nicer. There's some convention around it. But this is essentially what epsilon differential privacy is. And to think about it geometrically, well, remember, A is random, but remember, D is fixed, right? This probability here, this is talking about the probability, the randomness in A, right? There's no randomness in D. We're thinking about D as fixed, right? So we're kind of taking the view of like where you get a data set, the data set is fixed, the randomness is in the algorithm, right? So it doesn't make sense to talk about differential privacy for, a lot of the algorithms we talked about that are not randomized, because they're deterministic. But we've talked about at least one randomized algorithm so far, which is, for example, random forests, where it is a randomized algorithm. There is randomness in how the algorithm actually works. And so that's what this probability is looking at. So what does this mean geometrically? Let's suppose that the distribution, we have this distribution A of D for the possible outputs that algorithm A could produce. And this is a density, and these are the different values, and this is the most likely. And the distribution looks like this, right? It looks like kind of e to the negative x. It's sort of like a symmetric exponential distribution. And if A of D prime is kind of like shifted by epsilon, right? Like it's sort of like you can imagine like the distribution for D prime kind of shifts, right? Because the algorithm has the same distribution, but maybe it shifts by some epsilon. Then the ratio here, right? The sort of like, if I rearrange this, right, I can get, it's essentially the ratio of this divided by this is less than or equal to e to the epsilon. And that's exactly what this dotted line is just showing, that the ratio is bounded by e to the epsilon. And that's kind of the intuition, or that's kind of the math behind differential privacy. Next, we'll talk about some of the intuition behind it. So I want to talk about a common model that people use to think about differential privacy. And this is slightly different from what we talked about in randomized response. So here, the way this works is, you or the data scientist on the right has some query that they want to know, some interesting thing about some data set. And we'll call that the query. And they go and ask some curator. And the key here is that we have to be able to trust this curator to maintain the privacy of the data set, right? Maybe as, if anybody can go and ask these queries, then a malicious actor could use it to, de-identify, to conduct some kind of attack to, violate the privacy of individuals in the data set. But as long as we trust the curator, then any data scientist, any analyst can go and ask some query, and the curator will say, okay, I'll, run this query, run this algorithm on this data set, and I'll give you back the result, but I'm going to add in a little bit of noise, or I'm going to shift things a little bit or change things just a little bit. Why? It's so that, and I'm going to do it in such a way that you can't tell whether I ran it on like the data set D or a data set D prime, right? Where maybe there's one other person missing, or maybe there's one other person, new person, right? And this idea of you can't tell the difference between whether or not there's one more person or one fewer person, this is where the name differential privacy comes in, right? Where we're particularly looking at the difference between the data set and the data set with or without one person different. So this is kind of the model. This is slightly different from what we saw in randomized response, where we kind of push the privacy to the actual individuals being queried as part of the data collection. But a lot of times we have data sets that are gathered, in a non-privacy conscious way, right? Without something like randomized response. And so in that case, we have to find a curator. If we can find a curator that we trust to maintain the data, and we can, run these queries in some way, then we can guarantee this particular kind of privacy. Now, I want to point out that this isn't the only, just because we have differential privacy doesn't mean that everything's, completely safe and hunky-dory. You can imagine, let's say I use this data set to conclude that, I don't know, people who smoke are more likely to, have cancer, and then the insurance company finds out, aha, you smoke. They don't know that you're in this data set, but they know that you smoke, and then they use that to maybe charge you higher premiums for your insurance, right? And so just, the results that come from this data set can still be used to, do things that are potentially nefarious or potentially identifying individuals. It's just that the key here is that the definition says we can't tell whether or not a particular individual is in the data set. So now I want to talk about a way that we can actually achieve differential privacy in this whole query curator framework, right? Where if I'm running a bunch of queries and the curator has access to the data set, then I basically should not have the ability to identify if somebody is in any individuals in the data set. And so I'm interested in asking about some query, and I'm going to make an assumption, and that assumption is that if I run the query on a data set and then I run the query on a neighboring data set, then the results are going to be pretty close. In particular, they're going to differ by no more than one, which is pretty reasonable, right? If I'm taking the average of a large number of data points, then it should be pretty similar between running it on all the data and all the data with one person fewer. Okay, so this is my assumption that I'm making going in. And remember that the goal for differential privacy is to have some algorithm, dA of d, such that the probability that A of d is, in S is less than or equal to e to the epsilon times the probability that A of d prime is in S. Right? In other words, if I run my algorithm A on D, I run it on D prime, then the randomness in the algorithm, should give me a result of that's pretty close. That's within e to the epsilon. Okay, and so what I'm going to do is I'm going to define my algorithm as follows. So I'm going to say A of D is equal to Q of D plus Z. And what is Z? Z is just noise. And how am I going to define that noise? I'm going to define it such that the distribution of Z is e to the minus absolute value of Z divided by some parameter lambda. And the distribution looks something like this, right? This is essentially sort of like a two-sided or a symmetric version of the exponential distribution. And this is called the Laplace distribution. Right, and so that's why this is called the Laplace technique, because what we're doing is we're running our original query, right? I'm running my original query, and then I'm adding in some noise. Right, so I take the original query, I add in a little bit of noise, right? So I is the curator. So the curator is able to see the whole data set, see the original value of the query, but adds a little bit of noise. And the idea is that the noise is not going to be so much that it affects my analysis, right? I have this guarantee that the noise is not going to, make a dramatic effect, but it's going to be far enough that if I have this, difference between D and D prime, then the results should be very similar. And we'll show in discussion a little more about how and why this actually achieves differential privacy.